días tengan todos ustedes. Muchas gracias por la asistencia. Voy a cambiar a inglés. Desde que la plática va a ser en inglés, vamos a cambiar a inglés para presentar al profesor. So, welcome to this second seminar of the CERICOM, Centro Virtual de Computación. I'm going to introduce Professor Herlihy. So Maurice Herlihy has a bachelor in mathematics from Harvard University and a PhD in computer science from MIT. He has served on the faculty of Carnegie Mellon University and the staff of DEC Cambridge Research Lab. He's a recipient of the 2003 Dijkstra Prize in Distributed Computing, the 2004 Golden Prize in Theoretical Computer Science, the 2008 ISC Influential Paper Award, the 2012 Edgar W. Dijkstra Prize, and the 2013 Wallace McDowell Award. He received the 2012 Fulbright Distinguished Chair in the Natural Sciences and Engineering Lecturing Fellowship, and he is Fellow of the ACM, a Fellow of the National Academy of Inventors, the National Academy of Engineering, and the National Academy of Arts and Sciences. He has served as a consultant to several industry blockchain projects, including Facebook, Algorand, Ethos, and others. So we really thank you, Professor Herlihy, for your presence. It's really, we feel honored. It's really a pleasure to have you here at UNAM, and I thank you in advance for your conference. So I'm going to leave you with Professor Herlihy. Okay, thank you.
Well, thank you very much, and it's a great honor to come all this way to address the students of UNAM. So, as many of you may have noticed, Bitcoin is very much in the news. You know, every day there's a newspaper article about the Bitcoin, and it's usually always good news. It's kind of a fascinating subject, but it's fascinating in the way that when you drive down the highway and you see there's an accident, you look at the accident even though you know you're a bad person for doing this. Part of the attention that Bitcoin gets has to do with simple greed. This is the price of one Bitcoin measured over time. As you can see, about a year ago, it was almost 20,000 United States dollars. Now it's somewhere between 3 and 4. And if you're like me, you had friends who were talking about how great Bitcoin was and how rich they were becoming while the price was going up. And then they were silent, you know, while the price was going down. You can explain this and almost any other technical phenomenon by something called the hype curve, where something is invented. While it's new, everyone has exaggerated expectations. Bitcoin is going to need for government, lawyers, police, most of civilization, so we can live in a libertarian paradise electronically. Then people discover that much of this isn't true. Then they reject the idea and say, I feel angry and betrayed because you told me this was going to be so wonderful, and it isn't. And then slowly people learn how to improve things, and in the end it becomes a normal, boring thing. And so what I think we can say that the peak of inflated expectations was when Bitcoin reached this absurdly high valuation. Today, there's a lot of disillusionment where Bitcoin is worth a lot less. And our job is to make sense out of what's going on, to understand underlying mathematics and the science, to see through all of the sensationalistic news that dominates today's coverage. Bitcoin came to the attention of most of the public when the FBI closed down Silk Road. Silk Road was a darknet website where you could buy drugs, weapons, you could hire assassins, you could do all kinds of illegal activities. It made huge amounts of money, but all the payments were in Bitcoin. For a while, this was almost the only actual use of Bitcoin as a currency, was to conduct illegal activities on the web. And for this reason, Bitcoin has a little bit of a bad reputation. Another thing that contributed to the bad reputation was that certain exchanges, an exchange is like an unregulated bank. So if you have a Bitcoin, you want to keep it safe, you can hand it over to an exchange, and they promise to give it back to you. Except that about 2 or 3 years ago, there was an exchange in Japan called Mt. Gox where something like several $100 million US worth of Bitcoin went missing. And to this day, nobody knows. Was this stolen by the people who owned the bank? Was this stolen by organized crime? Was this lost because the people who ran the bank were incompetent? It's still mysterious what happened, but this did not contribute to Bitcoin's reputation as a safe and stable place to keep your money. There's a little bit of a comic opera aspect. So Bitcoin was invented by someone who called himself Satoshi Nakamoto. This is a very common Japanese male name. Now, nobody knows who Satoshi Nakamoto is. The only thing is we're pretty sure he's not Japanese. Half of the paper that he wrote is written in North American spelling and half is written in British spelling, probably to confuse people. But it's clear that this is a person who speaks English as a native language. Now, I said nobody knows who he is, but every now and then people show up and claim to be Satoshi Nakamoto. This is a little like the Russian Princess Anastasia, where people show up every now and then claiming to be that person. The lost Dauphin, the son of the French king who vanished after the revolution. Now, there's a lot of controversy, but it's pretty clear that the people who claim to be Satoshi aren't. But there's a lot of very unflattering arguments that go on about whether somebody is smart enough to be Satoshi, whether they're honest enough to be Satoshi, and so on. But this, in some sense, detracts from the dignity of the entire operation. Anytime you want to buy anything that's either illegal or embarrassing, you can use Bitcoin for this. Again, this is almost the only use. Nobody uses Bitcoin to buy a pizza or a car. Technically it's possible, but really doesn't happen. But if you're trying to do something, again, either illegal or embarrassing, then this is the way that people do things. Now, this is a cartoon that appeared in the New Yorker magazine. I don't know if you can read it, but this place sells tacos, and this place sells tacos on the blockchain. So this means that there's a lot of unwarranted hype, that if anything that you do, if you say it involves a blockchain, then people will get more excited about it, whether or not this is technically justified. But I'm not going to talk about Bitcoin as such anymore. I'm going to talk about blockchains. So blockchains are the technology underlying Bitcoin. Now, you can have an opinion about whether Bitcoin itself is going to continue to be important, or whether Bitcoin is the MySpace of currency and it will be taken over by other more technically advanced currencies. I'm not going to address that. What I want to do is put behind the sensationalism, the scandals, all the excitement, and talk about the technical merits of what's going on, and in particular how all of this new technology is really in some sense a disguised form of old familiar technology about classical distributed computing, that most of what happens in blockchains is a disguised form of familiar ideas dressed up in new language. So I want to talk about why we need real scientific work on this. So One way to think about this is when you build a distributed system, you're really worried about failures, or you're worried about unexpected timing. And the easiest way to think about this is to say that you're playing against an adversary. So there is someone out there who is trying to make your life difficult. You have to design your algorithms and data structures and systems so that you win the game against the adversary. So a classical adversary might control timing. You could delay messages. You could take a page fault and be slow. You could have a replicated database and some part of it crashes, and you want the rest to continue working. You could lose messages. At the extreme, you could have Byzantine failures. Byzantine failures were invented because people wanted to work with, say, sensors on airplanes, and they didn't know how they would fail, so they said, let's just pretend the worst thing happens. But they didn't really think that there was an intelligent adversary out there. They just thought, well, it's very hard to predict. So we'll say, what's the worst thing that can happen to a 2-bit register? So, and then we would, against such an adversary, you solve a mathematically clean, simple problem. For example, the well-known consensus problem. Now, today things are different. Today we have real hackers, real human beings who are working very hard to undermine your systems. This is not just crashes, not just lost messages. There are very subtle attacks. Meltdown is a way of reading someone else's memory by taking advantage of very complicated and subtle caching and speculation. Spectre is another version of this. Reentrant attacks, I'll mention briefly later on. These are all very sophisticated attacks. And the problems that society has to deal with are things like, how do you hold an election when someone else is trying to use very advanced techniques to subvert this? So in some sense, it's the same kind of challenge we had before, but it's much, much harder. And the enemy is much more sophisticated. So this is the paper that invented Bitcoin. This wasn't published in a conference. It was simply put out on it was published on a website somewhere. And what this illustrates is that real intellectual innovation usually comes from outside the community. So established scientists, established scholars, rarely come up with something that's really disruptive, because it's much easier to do incremental improvements in the work that we already know how to do. My short-term goal is to get a paper accepted to a conference where I can go and meet my friends and work on the paper for next year's conference. And writing a really revolutionary paper that is likely to be rejected doesn't make any economic sense for people like me. So we can ask ourselves, would this paper have been accepted to a mainstream distributed computing conference in 2008 when it was written? We don't know, because this never happened. But I suspect that there would have been difficulty. This paper has no mathematical theorems. This paper has no experiments. This paper outlines some crazy ideas that nobody would ever possibly implement. And of course, they did implement it. And it's now a multi-billion-dollar industry, and it has had far more effect in the world than any paper that was accepted in a respectable academic conference. Of course, I don't want to exaggerate, there are probably hundreds of other papers that were rejected that deserve to be rejected. But nevertheless, this is something to bear in mind. And what I want to talk about here is, this seems like a completely alien, different approach to doing distributed computing. And I want to argue that it's basically far more familiar than it looks. So here's how to understand the distinction. So the blockchain world is a kind of an alternate universe to the distributed computing world, where we can recognize the same features that we know, but they've changed in strange ways. sometimes in minor ways and sometimes in major ways. Sometimes we need to work to recognize that one thing is the same as something else. So I'll briefly talk about how consensus is very similar to proof of work. Concurrent objects versus smart contracts. I'm not going to have time to go into this in technical detail, so I'm going to kind of give you an impressionistic story, and if you're interested, you can pursue this. Now, Star Trek was one of my favorite TV shows when I was in college, so now you know how old I am. This was a cheesy 1970s science fiction series that was canceled, but then it became a kind of a cult show. Now, there is one episode where Kirk and Spock, the captain and first officer of the starship, they fly too near a star or something, and they end up in an alternate universe where they meet their evil doppelgangers. Now, you can tell these guys are evil because this one, he has a beard, and that one is wearing a muscle shirt. And these are universal signifiers of evil in the 70s United States. And so my premise is that this is the way to understand blockchain versus distributed computing. You can identify that they're the same people, but one is evil and one isn't. But basically it's more alike than you would think, and I want to explain what the similarities and differences are, because I find this is the easiest way to understand this field, which might seem at first very confusing, is, to me at least, starting from the classical distributed computing and moving forward from there. Now, I became interested in this when somebody gave me a paper for a company that had just raised tens of millions of dollars in funding, and they were doing Byzantine agreement, and I read the paper, and after the first page I realized these people don't know what they're talking about. They're using terms incorrectly, their algorithms are wrong, and yet they just raised a lot of funding. So at that point I decided this must be an interesting area because the bar is low. And early attempts to build distributed systems in the blockchain world didn't work out very well. Now this has changed. These systems are now much more stable. They fixed many of the bugs, but the people who did this are very smart, energetic people, but they didn't actually know very much about the background and the history, and so they made a number of elementary mistakes. Now, I don't want you to think that I'm being supercilious, because the academic distributed computing world did not build, this blockchain economy. This was done by kind of non-academics, not by respectable scientists and so on, but by mostly young people who had maybe a little bit too much money and a little bit too much ambition, but the accomplishment is real. So I don't want to sound like I'm complaining about the young people these days. It's really much more complicated a picture. So the basic idea behind blockchains is very simple. There's a lot of mystification, but really a blockchain is just a ledger. A ledger is basically a log of events. Ledgers of this kind were invented during the Italian Renaissance. Double entry bookkeeping, all of these things. They're responsible, arguably, for the invention of capitalism, because you can organize large companies and ship goods across the world. And what it is, it's an append-only list of events. You cannot go to a ledger and erase something. If you want to correct something, you append a correction. If you're working for a company and you catch somebody erasing something, you should probably call the police, because that's not a good sign. You can only append. It doesn't have to be financial. The word ledger suggests that it's always money, but it could be a file system. It could be an operating system. It could be, a log of messages that were received. It's any kind of events whatsoever. But the important thing is that everyone agrees on the content. You and I might not trust each other, but we have neutral protocols for agreeing on what the ledger says. So if there is a disagreement, it's because one of us is dishonest. And most of all, it's tamper-proof. There is no practical way you can go in and change the ledger after it's been written. All of these things are important, but this is really all that you need to understand about ledgers. There's a lot of complexity on how you implement it, but this is the abstraction on which everything is built. In Bitcoin and in classical distributed computing, there are mechanisms called consensus on one side and proof of work, which are almost but not quite the same thing. So literally, this is what a blockchain looks like. So it's an event pointing to another event pointing to another event. So this is first level implementation of how you would build a ledger. Now, in order to make things tamper-proof, we're going to use a little bit of cryptography. So here the idea is we have something called the hash function, which says it's easy to go from the thing that you care about to the hash, but it's very hard to go the other way. So you can think of hash as a unique fingerprint. So we're going to add to this record, I'm going to take a hash of the previous block, which in turn includes the hash of the other. Everything is kind of linked together. And this has the nice property that if I go in and I try to tamper with something, I'm trying to steal something, I change a bit, then the hash will be wrong. And there's no way I can go back and change the hash to match the new value, and that will percolate all the way through. So that if anybody changes as much as 1 bit in the log here, then everyone will instantly see that there's a problem and reject it. So this is the key to making things tamper-proof. So even more literally, if you want to build this sort of thing in the context of classical distributed computing, you keep this list of things that happened. I didn't draw the hashes because I didn't want the picture to be too complicated, but the hashes are there. And then we have something called consensus, which takes in all the things that want to happen and decides which one goes next. So consensus is just a way of saying these 3 things all want to get in line, pick one, pick one, pick one, and put them in order. So, the technical definition is a little bit more subtle, but it's basically, pick one. This has a nice property that this is a simple list of things, and all of the magic, all of the clever algorithms go into this consensus box, which is completely generic. This kind of design is for anything. Now, the oldest blockchain in the world is not Bitcoin. The oldest blockchain in the world was invented in the 1990s. And the idea there was suppose you invent something for a laboratory, but you don't want to publish it, but you want to prove later on that you had invented it, you take a document where you declare your invention, you hash it, and you publish it in the New York Times. So you store the secret documents on the server, and every day you take the hashes of the document, and you publish it in the New York Times Lost and Found. It's the cheapest kind of ad. And so later, if somebody challenges you, if there's a patent dispute, you can say, yes, I invented this in 1997. Here is the hash published in the New York Times of 1997, and here's the document that hashes to it. And that's proof that you had the document without having to reveal what the document is. And this is basically the way Bitcoin works. Okay, so let's look at a use for blockchains. So let's say our friend Alice has a frozen yogurt business. Frozen yogurt was once very trendy, but her business is in trouble. And this trouble happens because when she receives shipments of yogurt from the factory, they're melted. And so she needs to try to figure out what's going on. So she looks at her supply chain. So her supply chain consists of 2 things. There's Bob's truck, which transports the frozen yogurt from the factory. And then there's Carol's factory, where the yogurt is produced. And somewhere between the factory and the delivery of the truck, the yogurt is melting. So she goes to Bob and confronts him, and he says, okay, first off, I never transported that yogurt. Plus, it was melted when I got it from Carol. And third, it was fine when I delivered it. And, lawyers are perfectly happy to argue in this kind of a style. And Carol also repeats the same thing. So Alice has no way of knowing what is going wrong with her supply chain. So she says, okay, what I'm going to do is I'm going to build a ledger in the cloud. I'm going to give permission to Bob and Carol to write to the ledger. And I'm going to buy a bunch of sensors, temperature sensors, and I'm going to put them in the trucks. I can tell what the temperature is. So I'm going to take this and turn this into what's almost a blockchain. Not quite, but it's very close to a blockchain. So every 10 seconds, the sensors are going to make a sensor reading. We're going to use consensus to figure out, maybe take the average of these sensor readings. And we're going to record the temperature at every 10-second interval. So if the yogurt melts, we'll know when it happened. We're going to have Bob and Carol sign when custody goes from Carol's factory to Bob's truck. They both sign the handoff. And so in this way, now Alice has a way of telling what happened. She knows who is responsible for letting her yogurt melt, and she can, for example, take that to a court and sue. So this is not cryptocurrency. There's nothing here that is really radically new. We're putting together well-known pieces, but what we have here is effectively a blockchain. It's not distributed yet, but it's still very much what blockchains do. Okay, so now let's take this from a kind of half blockchain to a full blockchain. So Alice decides to sell her frozen yogurt business and open a restaurant. Now the problem with opening a restaurant is that it's capital intensive. You've got to buy a deep fryer, you have to buy plates, you have to buy forks, and you have to pay rent. Venture capitalists are greedy, they want too much, so she decides she's going to raise money by herself. And so what she does is, not really an initial coin offering, it's a coupon offering. So what she says is, okay, if you give me money now, I will give you a coupon that you can redeem for a free meal later on. So you give me money which I will use to buy a stove, and then 6 months from now you can come to my restaurant and I'll give you a free food or discount food. And so, of course, being media savvy, she doesn't call it a coupon, it's a crypto coupon. But she's going to put this on a kind of a blockchain. So what I'm building here is basically, I'm inching over toward a Bitcoin-like blockchain. And the idea here is that she's not selling stock, she's selling a promise of future delivery of service. And in this way, she's trying to get away from a regulation, probably unsuccessfully. In order to go any further, I'm going to give you a 30-second introduction to modern cryptography. I apologize to everyone who already knows this. So everybody has a public key and a private key. You can tell your public key to anyone. You keep your private key to yourself. If I take a public key, I can take a message, I can encrypt it, and no one can read it. It can be decrypted. Sorry, if my public key, you can read it, you can decrypt it with a private key. And in this way, I can produce a message that only Alice can read. So you can take my public key, encrypt it, send me a message, and only I can tell what that message is. So you can securely communicate with me or with Alice. The other way, if you take the private key, Alice can take clear text, she can encrypt it with her private key, and anyone else can check and make sure that it decrypts. Only Alice could have produced this document, so that's a digital signature. So in this way, you can sign a document in a way that only you can do this. Now, how are we going to use this? Well, we're going to use this to create and sell coupons. And for coupons, you can think Bitcoin if you like. So I I don't know how many people here are familiar with the story of King Arthur and the sword and the stone. So this is the, in kind of archaic English, whosoever pulleth out the sword or the stone and anvil is rightwise king born of all England. I love to say that because it's so poetic. So in this case, the sword is a public key. This is out there, everyone can see it. The private key is the ability to pull out the sword. So you look around, I don't know which one of you is the future king of England, but if you want to prove you're the future king of England, all you have to do is come up and pull out the sword. In the same way, you can take your private key and decrypt things, or you can sign things, and prove your identity that way. This is what this authorizes you to do, is become king of England. Of course, this isn't actually what blockchains are supposed to do. So when Alice goes to build her blockchain to sell the coupons for her restaurant, she's going to use public and private keys in this way. So what the entry on the ledger says is that anyone who knows the private key matching the following public key is the owner of a crypto coupon. So being on the ledger makes this authenticated, or makes this real. The public key allows the owner of the coupon to be recognized, and the private key conveys ownership. You demonstrate that you know the private key, gives you ownership of this coupon, which allows you to show up later for a free meal. And this is what you can do. You can't become king of England, but you can get a free meal. If you want to spend the coupon, so if I own the coupon, then I should be able to give it to someone else. When I'm done giving it to someone else, they should be able to prove that they own the coupon. So I'm going to put another entry on the blockchain, which says that the public key allows the owner to be recognized. So if I wanted to give a coupon to Sergio, I'll put Sergio's public key on the blockchain saying, this is the person. We can prove he's the person by proving he knows the private key. And what's being authorized is that I'm giving him now the ownership of the key. So by tracing through all of these entries, I can figure out who the latest owner of each coupon is. I can even break the coupon into two pieces and give fractional coupons to people. So this is basically the way Bitcoin and other cryptocurrencies work. Now, Alice doesn't actually want to build a data center to maintain these crypto coupons. That's expensive. Customers might not trust her to do that because, after all, she's supposed to provide the meal. She could pull the plug and then not have to feed anybody. So she has this brilliant idea that she's going to crowdsource the blockchain management. She's going to get other people to do this for her. Now, other people aren't going to do this unless you pay them. So what is she going to pay them with? Any guesses? He's going to pay them by giving them more coupons. So this is the kind of brilliant circularity of crypto coupons and cryptocurrencies in general, is I want you to do the work for my cryptocurrency, and if you do this, I'm going to pay you with more of my cryptocurrency. And somehow, this all works. So she's going to create more coupons to the people who run the blockchain. Now, who controls the blockchain? We can do this in a centralized way, the same way that Visa and MasterCard do things, or we can do things in a decentralized way where we have a bunch of people who are all running the blockchain and they can vote or do something. Voting is an interesting idea. So let's say, I'm going to borrow all of your laptops, and then you can vote on what happens to each coupon. Now, the problem with voting is you're not always sure who is voting. Not everybody might at first seem to be. Now, in classical distributed computing, if you want to make distributed decisions, you have to vote. So this is the good Spock says, voting, decision requires voting. The evil Spock says, well, let me introduce you to my friend Sybil. So the technical term for what I'm about to describe is a Sybil attack. This is a picture of a Sybil from the roof of the Sistine Chapel. There's no relation between the Sybil of Sybil attack and the Sybil of the Sistine Chapel, but it's the only picture I could find that made sense. And when you vote in the United States, they give you a sticker that you can put on your shirt. And our friend Sybil likes to vote a lot. And so the problem here is that if you don't know who is out there, it's easy for one person or organization to create a lot of fake accounts and vote. So I want to steal some coupons, so I will create 1 million fake accounts, and they'll overwhelmingly outvote all the honest people. So we need a way to control. We need some symbol that's hard to fake. Now, this is a well-known problem in biology and sociology. Well, imagine that you want to run a street gang with doing all kinds of nasty illegal activities, and somebody comes along and says, I'd like to work for you. How do you know that they're not a police officer? How do you know they're not a journalist? How do you know that they're not just lazy? Well, typically what you ask them to do is you say, do something that's kind of expensive that you wouldn't do if you weren't sincere, like get a tattoo with the name of the gang. That isn't something that somebody who isn't committed would do. In nature, if you want to find a mate, you want to convince your mate that you have good DNA, you develop something like this, which says that, look at me, this is really attractive to predators, but I have been able to escape being eaten by an eagle for a long time, even with this beautiful tail. Therefore, I must have good genes. For various subcultures, I'd say, well, I'm a dedicated a punk, and I'm annoyed by all these high school students who want to pretend to do the same thing. So unless you get a tattoo on your face, which is going to annoy the hell out of your parents, you can't join. So this is exactly what proof of work is. It's the equivalent of getting a gang tattoo. So I'm not going to talk about the technical ways in which this is executed, because you can find that out for yourself. But the basic idea behind proof of work is you consume resources for no purpose other than demonstrating your sincerity in running the blockchain. Now, one way to do this is to say, if you take a $100 bill and burn it in front of me, I'll let you vote, which is basically what proof of work is. Now, the interesting thing about this is it makes Sybil attacks pointless, because burning $101 bills is the same as burning a single $100 bill, so there's no point in pretending to be many people, because you have to consume more resources. So let me get a little bit more detailed. This was invented as a way of controlling spam. Never caught on, unfortunately, and it's been adapted to a proof of work consensus. And again, it's expensive to fake. So the way to think about this is we're going to hold the lottery to decide what is going to be the next coupon transaction. Tickets are expensive. This is the proof of work part. So if you want a lottery ticket, you have to burn a $100 bill in front of me. But all you get for this is a lottery ticket. So 5 of you all burn $100 bills. Okay, here are 5 lottery tickets. And you don't get paid right away. You only get paid if later winners endorse what you did. So if you try to cheat in some obvious way, you won't get paid. So you have an incentive to behave yourself, even though we don't know who you are. And that makes Sybil attacks expensive and pointless. And so really, this is all you need to understand about proof of work, unless you actually want to build your own blockchain, in which case you can look up the technical details. But this is really what's important. Okay, now there's a problem with any lottery, is that every now and then, 2 players simultaneously win. This is infrequent but not rare for lotteries. And when this happens in a blockchain, what happens is you have 2 people, okay, this transaction, no, that transaction. And the later winners are going to decide which one to build on, which one to hash and to refer to. By the time this starts, you don't know who's going to win. So What this means is that if you see something is on the blockchain, you want to be a little careful because it might be displaced by something else. If you want to buy a pizza from me, you put your Bitcoin on the blockchain. I see it's on the blockchain. I'll say, okay, that's okay. I'm not too worried. The worst thing that can happen is, I lose, the value of a pizza. I'd rather give you the pizza now. But if you want to buy a Tesla, I'm not going to ship you the car as soon as that appears, because if your transaction vanishes because someone else's transaction also won, then I can't get the car back. So typically what happens is you cannot ship something until you're absolutely sure that the entry on the blockchain is not going to be displaced, which means basically you've got to wait about an hour in the real world before you can be sure that a payment is real. Now, this is different from the classical notion of consensus. Classical notion of consensus, everybody comes in and says, me, and then the protocol picks one winner. In proof of work, there could be multiple winners. Usually not very many, usually not for very long, but you have to be aware of the fact that because someone appears to have won consensus, that doesn't mean they really did. You need to wait long enough to be sure that this happened. So there's an uncertainty that you don't see in the classical world, and this has implications. Among other things, it means that commerce using Bitcoin is going to be slow because nobody really trusts the recent entries to the Bitcoin chain. By the time something is far back enough, it becomes really, really unlikely that it will be displaced, and it's probably safe to do anything. But for something that is recent, you have to be careful. Similarly, in classical consensus, if you win, you win, and nothing will change that. Consensus, there's still a matter of dispute. You can have two chains building off the same one, and you might have to wait to see which one wins. Because of communication, asymmetries, and so on, there can be transient disagreement as to the state of the chain. And again, this complicates things in the blockchain world, but I think it's still the right way to think about this is it's consensus, except that it's only gradually permanent instead of instantly permanent. Okay, so the last thing I'm going to cover are something called smart contracts that you may have heard of. A smart contract is a script that runs on the blockchain. A smart contract is not actually a contract, and it's not very smart. Smart contracts is a marketing term, which has stuck, so I'm going to use that. A smart contract, let's say we want to hold an election on the blockchain. So a smart contract is very much like an object-oriented programming language. Don't bother trying to read the actual code. I'll tell you what you need to know. Here, for example, we have a ballot. You manage some long-life state. This maps each voter to the thing they voted for. A function is basically a way of reaching in and calling the contract. Here, if I want to vote, I call this a function, and I say which of the proposals I want to vote for. And contracts can call each other. This model looks single-threaded. There's only one thing going on. And I'll skip this part. Now, here's an application for smart contracts that actually happened. DAO, pronounced DAO, is a Decentralized Autonomous Organization. This was a hedge fund with no managers. The idea here is that it would invest. You would invest in the DAO. Everyone would pool their money, and then they would vote on who to invest in. The smart contract would tally the votes and disperse the money. This means you don't need administrators. You don't need anybody other than the investors and the people who write the smart contract. No board of directors, no lawyers. It's controlled entirely by smart contracts and investor voting. And the claim here is this phrase, code is law. You need lawyers, you don't need courts, because the contract will execute. We know what the contract is going to do because everyone can read the code and we all agree. And so this is kind of a libertarian paradise because we can make agreements among ourselves. We don't need the apparatus of the state or anything to make things work. And of course, when this came out, there was a lot of excitement and hyperventilation. People were saying, oh, this is great. All those Wall Street parasites will now be driving Ubers. And, finally the people can take control of high finance. And so this went on for a while. So let's look at a very simple piece of code that is almost the same as code they actually ran. So this is a function that says, I want to withdraw some of my own money. So that function is called withdraw. You say how much you want to withdraw. The green arrow shows the line that we're executing. First we say, well, okay, so who's calling? Again, never mind the idiosyncratic syntax. Just says, okay, so who are you? Does the client have enough money? Is the client's balance greater than or equal to the amount that they want to withdraw? If so, send them the money. So send money is called to the client's contract that actually transfers money. So it says you have enough money, go ahead. And the result of and I'm not hiding anything. So let's rewind and figure out what happened. So here we are, we're transferring the money to the client. So this is the client's smart contract. So we're calling this, and the client credits its account, and then there's something weird. Wait, what? It goes back and it calls the first contract again, but without returning. So it makes what's called a reentrant call. So it goes back up here and it calls this function while it's already active. So now we have two program counters. We have the gray one, which is suspended, and we have a green one that's active. And this is the interesting part. It comes down and says, does the client have enough money? Well, of course the client has enough money because we haven't debited the first withdrawal. It updated the book and didn't realize it was vulnerable to code again. So you can send money again and again and again and drain out all of the money regardless of what your account balance is. And this actually happened. Sometimes it's 50 million, sometimes it's 60 million, but it's a lot of money. This had all kinds of bad effects. And how did they fix this? Well, the fix was they went and they basically said, okay, we're going to change the rules. They went and they changed the code of this allegedly decentralized currency and said, okay, everything is normal except anything having to do with the DAO, we're going to pretend it didn't happen. So they're basically rebooting the currency and starting over from the time the DAO was created. This is called hard fork. And this whole code is law thing, which we're very militant about when they're setting it up, that if you lost your own money, then code is law, libertarian paradise and all that stuff. But you steal the money of the people who run the place, and suddenly the rules, code is no longer law. So I'm not saying this was the wrong thing to do, but I am saying that when people tell you about all this libertarian ideology and code is law and decentralization and so on having to do with blockchains, you should be very cynical, because in practice, that doesn't really work. Okay, from a scientific point of view, when this happened, what the proponents of blockchain said, this is a new field, we had no idea, this is such a new and exotic area. But in fact, this is a classical synchronization error that I teach my undergraduates about this in my structures class. If you change the name, they would recognize this instantly. I'm not going to go into what exactly it is because that's a little bit technical and I'm running low on time. But if people who did this had taken my class, they wouldn't have made that mistake. Okay, so what I tried to do here is to demystify the technology behind blockchains a little bit. I still believe that blockchains are going to be very important. I believe cryptocurrencies are going to be important, maybe just not Bitcoin. But I wanted to warn you about the mystification. I want you to take a somewhat more cynical view. You know, it's odd to be instructing Mexicans on cynicism, but you should take a more cynical view of cryptocurrencies than the proponents will give you. So what I want to contrast a little bit is the philosophy behind blockchains and Bitcoin. This is something where I have a lot of sympathy with many of the ideals, but of course ideals can be dangerous if they're not executed well. So on one side, people say, well, cryptocurrencies and blockchains are great because they're resistant to censorship. No government can suppress Bitcoin. They can make it hard for you to use it, but they can't destroy it because it's replicated in so many places. You know, the police come in and they tear out one server, you know, there's a million more. The government can't decide, oh, we're not going to allow this person to do commerce because, you know, things are done anonymously through cryptographic keys and so on. So, you know, that's actually a noble goal. A trust-free society says we don't need centralized organizations like Visa and MasterCard basically spy on us. You know, Visa and MasterCard want to know a lot about you to know whether they can lend you money. And in some sense, if you have centralized gatekeepers like this, they have to invade your privacy in order to stay in business. And there was a vision of if we could decentralize all of this and get rid of these centralized financial institutions, then our privacy would be much stronger. The idea that code is law says, well, we can get rid of lawyers and much of the justice system because smart contracts can deal with everything. Now, it's true that smart contracts can deal with a lot of routine things. So a smart contract could, for example, say, issue an insurance policy to a farm and say, if you get less than so many centimeters of rain, we'll pay you. Then all you need to do is the blockchain observes how much rain fell and disperses the money. If there's a dispute, however, then you need a court because, you know, things get complicated. No algorithm can decide who is correct. So code is law is kind of an incremental improvement on the margins, and I'm not saying it's worthless, but it has been greatly oversold. Now, on the other side, code might be law, but we can't write correct code. So people who wrote this code that caused the DAO to crash were partly people who invented Ethereum. So these were the smartest, most expert people on the planet to write code, and it didn't work. You know, they learned quickly, and nobody's going to make that mistake again. But we can't really write code that everyone actually understands what it does. In order to do that, we need to have much stronger formal verification, proof techniques, and so on. So in some sense, this is a great advantage to people working on formal methods, people working on programming languages, and so on. There are great challenges ahead to make this work. And someday it will probably work, but it doesn't really work all that well right now. Okay, so here's my conclusion. So despite the fact that I have been telling you all kinds of cynical and negative things, you know, I do believe that blockchains are going to revolutionize how we do commerce, not just for currencies, but other financial instruments, for things like supply chain, like the frozen yogurt, for things like legal documents. You know, you can record who owns land on a blockchain. You don't need to go through inefficient or corrupt agencies to establish that. There are many, many possible applications. They're all being worked on by various companies. And to understand this, the best way I found is to say that the blockchain universe is not really as new as it seems. Really what's going on is they took a lot of pieces from classical distributed computing. They put them together in new and creative ways. They didn't really invent anything fundamentally different, but the combination of these kind of known pieces turns out to be very powerful. They changed the terminology to make it almost unrecognizable. Once you see through this and say, oh, I recognize that this is consensus except that it lacks the same kind of degree of finality, then it becomes much easier to understand. It becomes much less mystifying. This is a great area to do research. One of the problems with distributed computing is we came up with all of these very elegant algorithms, but nobody was interested. Now a lot of people are interested because we found something really powerful to do with it. So I think any kind of computer science or engineering that you're doing, you stop and think, is there some way I can apply this to blockchains, because there's a huge amount of interest out there and potentially a huge impact. And as long as you approach this with open eyes, then I think this is a great place to be doing research. And with that, I'll take questions.
Preguntas.